Today's major topic that I want to cover is not robotics, but it is going to be systems engineering. And this is a presentation that is mostly by NASA, but this is important because when it comes down to all the robotic systems in the future, you're going to be given a solved problem, either mechanically or electrically. And the big problems for solving will be software and general operation and control. So you saw there were those mechanical vehicles, or the bipedal autonomous vehicles. You are going to be working with the LabVIEW Danny robotic vehicle. So these are solved electrical and mechanical problems that you might just add some things onto. But it's a good idea to get to know and understand what is the entire system. So let's talk about what is a system and what is system engineering. By the way, how many of you have been through senior design already? All right. You've already seen this presentation or something similar? We'll go through it anyhow because there will be questions on the exams coming up. Things like using system engineering techniques, write the requirements for this robotic system. So this is, I'm trying to get into the more system approach rather than individual nuts and bolts of movement. By the way, in our guest lecture next week, Adam Harris will be doing a presentation on wheels, and specifically he'll be looking at how to do computation on how far you actually have to go when you're turning wheels, if you're turning this one in a clockwise, this one in a counterclockwise. So we're going to look at details a little bit lower. So let's start high up and go down a little bit. So simply stated, what is a system? Think, by the way, these notes will be available after class. They'll be out there. A system, it is an integrated composite of, and this is important, people, as well as products, processes, everything that combines together for some sort of single entity that has a specific stated need, specific job to do. So one example that I'm going to go through is the space shuttle. You know, since this is a NASA presentation, we'll look at the entire space shuttle when it used to be a system, or when it used to be a viable system. So if you think of any other types of systems that you have, well, that right over there is a camera. So you can think of that as a single aspect of a system, that being a device that you can sell or buy. When I worked in the cell phone industry, we had to look at everything associated with the cell phone. Sure, the only thing you really see is the phone itself, but underlying all that is, of course, the software associated with it, the electrical and mechanical hardware. When you buy it, you typically get it in a box that has instructions, that has a user's manual, that has a charger and a cable. So all of those different things are put together. Now, before you even get it, this device had to be tested. So now you have people and test processes for verifying that it's going to be made. And oh, by the way, you're manufacturing something. So you're going to have manufacturing processes, raw materials, that will all come together to generate a final product that you can buy. So, again, personnel, facilities you might have, processes, and hardware associated with anything. So, here's an example of a system. Space Shuttle has main engines. Now, a main engine, of course, is a collection of parts. And yeah, that is me, and that is a main engine. I had the opportunity to work for NASA one summer, and we got to go into the BAB, what is that?
Vehicle Assembly Building.
Oh, Vehicle Assembly Building. Is that what they call it? Oh, yeah. I had other pictures. You know, for example, I was able to reach up and touch the bottom of a space shuttle, you know, with all of its tiles, some of them off because they had to replace them. So I like that. I had a comment from somebody saying, I don't think that engine could even blast me off into space. So the engine is a part of the entire orbiter. So now you're looking at something, you know, for all intents and purposes, this engine is a system. Because look at it. There's the outside mechanics. You see right here there's a lot more associated with just the nozzle itself. There are the engine aspects. There's electronics, or I should say electrical systems on that. And then, of course, the people to build it and to do all the cleaning with it. But here we have a complete system, and they can test that separately. But when they take it and they put it into a space shuttle orbiter, now you have a subsystem that goes into a larger system. Well, also go a little bit further and say, all right, this orbiter has 2 solid rocket boosters and an external fuel tank all put together, and all of those individual pieces make up a bigger system. And then you think about it, well, if you're going to have this space shuttle orbiter with the solid rocket boosters and all, and you put a payload in it, and then you have the launch pad, the mission controls, all the people associated with assembling it to train the astronauts, etc. That's one system too. And then you could have a system of systems even higher up. The space shuttle goes up to the International Space Station. There are transmission satellites up in space that will take transmissions from the space shuttle, send them back down, etc., etc., etc. So, as you can see, systems are pretty much anything you want to enclose and identify that this is something that's going to be delivered. So, what is systems engineering? Systems engineering is delivering a system. There's all sorts of aspects of that. For example, you're going to design a system. You're going to create it somehow. You're going to operate it, and in the end, you're going to finish it. In other words, you'll put it to sleep. You're done, like the space shuttle system, right? They're no longer flying space shuttles, so that's done. But this is important. When you're doing systems engineering, you have to do a lot of upfront work. Specifically, you're going to identify what the goals of your entire system are going to be. You have to bound what this is going to include. You look at alternate designs. In other words, is it going to be a rocket that looks like some of the older space shuttle or the older space devices? Or is it going to be a space shuttle-like device? Something that is a plane that could cruise back to the Earth. You have to look at performance. In other words, the space shuttle, one of the requirements was reusable. This is the Ares, the ill-fated Ares program where you were going to fire it up into space and not reuse it. Now, not only do you have to design things, but you also have to verify the design, then you typically build it, implement it, and then you have to verify what you build. Now, with anything, and this is the last point here, anytime you build something, you have to assess whether or not it was successful. Or anytime you design anything, you have to identify if it met the specifications. And this is really important when you think about a robotic system. So let's say I have my little humanoid bipodal or bipedal robot that you saw earlier in the video. What were some of the requirements I probably had for that? Just put out one, just make some suggestions for requirements.
Degrees of freedom.
All right, so it's going to have n degrees of freedom.
N amount of sensors.
It's going to have m sensors.
K amount of legs.
It will have
Appendages.
I'll say 2 legs, all right?
2 hands.
What about an operational requirement?
Voice.
Have voice.
Battery operated.
The robot shall have degrees of freedom. So this is requirements A, B, C, D, E. Have voice what? Output?
And recognition.
Recognition.
Have voice recognition.
Battery power.
Have battery power
A life cycle.
to run
About
1
life
hour.
cycle.
Stability control.
Have stability control to allow it to
Balance.
walk
Must be life size.
and stand.
Should be
B,
life.
C, D, F, G, H, I,
Should be life.
B,
Life size.
life size, i.e.
5 foot, 8 inches.
2.0 meters tall. I like big, tall robots. They're more menacing.
Yeah, that's like 6.5 feet.
Yep.
Is that other program?
All right, so this just gives you an idea of it. But notice one of the things I said about this is assessment of how well the system meets the goals. So these are some of the goals. And is it easy to measure how many degrees of freedom it has?
Yes.
Yeah. Sensors, yes. Legs, yes. Voice input output, yes. Battery power to run 1 hour.
Yeah.
Yeah.
Obviously you're going to need to run it many, many, many times, right?
Yeah.
Stability control to allow it to walk and stand. Obviously you're going to need to have it operate in different types of environments. And in fact, this one requirement right here will probably require you to identify specific test cases and further requirements to say, how fast should it go? How many times will you allow it to fall over in an hour when it walks on its own? What sort of incline should it be able to walk? These are all types of requirements that you need to be able to identify for your robotic systems. Now keep in mind, we just wrote some requirements here, right? You're going to see this later, I'm sure, on a test. Hint, hint. All right?
Yes.
Yes. Even though it says this approach is iterative, there are different ways you can design this by building a prototype, going through all these steps. The prototype looks about what you want, then you basically redo the entire thing for a production system. One example of that would be that little robot that you saw. I'm sure they made a prototype to verify that they would be able to make hundreds of these things. Because wouldn't it be horrible that you spend all your time making the first one and then when you went to go make the second one, you couldn't recreate it. So again, several increases of resolution and where you're going into deeper and deeper design aspects, requirements, design, details, verification plans, costs, estimates. So, the concept of project management is parallel with systems engineering. And actually, it's a symbiotic relationship. But historically, project management is more concerned with planning, applying, controlling the use of resources. In other words, it's to set the fertile ground for the engineering work that systems engineers will do. And the systems engineer will follow a disciplined process or disciplined approach to be able to produce some sort of project or some sort of product or system that you want to do for your final goal. And again, the system engineer is typically somebody who will drive the design, the development, final production of some sort of system. The project manager will make sure that the system engineer has a lot of resources to do that. To give you an example, when I worked for Ericsson, I worked side by side with a system engineer. He had concerns with the software programming, the electrical aspects, the mechanical aspects of the phone. And as project manager, I made sure that he had all the materials to be able to build prototypes, that we had building facilities or manufacturing plants to be able to do the prototypes and the final production. And I also was the one who coordinated documentation and final delivery to our customer of these phones. Now, why did some of this originally come out? Well, what you'll often find, a system engineer is somebody who can pull together a whole bunch of different people to make sure that you're all focused on one aspect of your project, or all aspects of the project, and that there are no interfaces that don't mesh with each other. For example, if you are building a space shuttle, it would probably be really useful if you had a space shuttle that would fit most of the payloads that you want to send up. And so you would have to have a system engineer overlook all of those aspects of engineering, both the space shuttle and the payload. That's a silly one, it'll be on there. Man, I tell you what, I see some people that are getting really tired here. So let me take a 5-minute break, if you could pause that for me, and we'll come. All right, this is a continuation of our systems engineering lecture, and systems engineering is called different. It means something different to different people. So, for example, here we have a systems engineering group, and their idea of systems engineering is more of delivery of materials and ensuring that resources are available on time. Kind of more of a project management aspect to it. Others, for example, if you take the NASA attitude of it, it is combining electrical, mechanical, civil, and computer engineering, as well as manufacturing engineering, together for making a specific product or system. But system engineering as a discipline is gaining more and more traction, and is actually something that, even though you can get a degree in systems engineering, it usually works out better that you get a degree in some other engineering discipline, like electrical or mechanical engineering. Learn your discipline very well in the workplace, and then move up to being a system engineer, somebody that understands several different disciplines. And that's where, for example, the system engineer I worked with at Ericsson was actually an electrical engineer by degree, and he became more and more experienced in all aspects of a mobile phone, and so he was able to be the design manager of an entire mobile phone. Here's another nice thing, is a system engineer has a view of all the disciplines, and typically has a view of multiple projects as well. So they can carry with them a lot of lessons learned from all the previous projects. This is a slide I'll just put out there for you to read, a failure in system engineering. So, you've probably seen this before. How do you start a design? The best way to start a design is to reduce your entire product into smaller pieces. We've seen this before in senior design at something called a work breakdown structure, where you say, okay, remember this little robot we talked about? The walking bipedal one? What are the different pieces that you could think of for that robot?
Housing.
The what?
Housing for robot.
All right, so we have the mechanical housings of them.
Electrical.
All right, we have the electrical motors and
Sensors,
processors and controllers and stuff like that. What else? Well, the motors we included in electrical.
Computer program?
All right, the software to make it run in the first place. And maybe one more could be power system. Could be even a subsystem of the entire electrical. And so what you'll do is you'll reduce your entire project into smaller pieces. And it might be in different phases, it might be different subsystems altogether. And then you could work within those subsystems, defining them even smaller. And what you do, again, it's a lot easier to build something if you work with a little piece and then build it up and up and up. You had an example of this with your robots, right? You're probably worried about, how am I going to get these wheels to move? So you built the wheel enclosures or the wheel assembly, and then you figured out, okay, now how am I going to attach the sensor? So you're looking at all the different pieces, you're reducing it into the smaller components, and it's a lot easier to divide and conquer that way. So as an example, an aircraft system, and again, we're talking about an entire system. So it is not only the vehicle itself, which has airframe, propulsion, system software, automatic flight control. So even there's different parts of software in there. But it is also training. It is also data, in other words, design data and test data. It is also industrial facilities, you're building it. And then if they're building an airplane, they have to worry about repair later and making parts available. This is a pretty ubiquitous chart identifying how you're going to do your design for a system. So in other words, you identify your requirements, you allocate those requirements to different subsystems, functional subsystems, and then you synthesize and design those subsystems. At the same time, you have oversight in your analysis and optimizing and control. So this requirements list, or loop I should say, identifies, yes, you have to say what you want to do up front. And that's a very important part of systems design. What are you going to do? What's important for this system? That bipedal robot, we wrote a couple of requirements already. Some of them might be a little bit more in the synthesis and design. For example, it said have M sensors. Maybe you don't need to specify that way up front. You just need to have sensors that will identify how much a motor has turned, or the temperature, or that you will have a sound sensor. But most important, as I said, understand the requirements and how they will affect how you design what you put into there and how long it's going to take to design your system. I'm looking to see how much further I need to go, and I think I'm going to go to a couple more, and then we're going to have our demonstration of LabVIEW upstairs in the lab. So, in fact, I will make this my last slide. How many of you have seen this before? All right, just a couple of you. This is the standard V model of design, and actually, I've seen U.S. government documents where they have one V followed by another V followed by another V followed by another V, because each V has a nice way to say, up at the top is things that are rather general, and you keep on going down and dividing functionality, getting more detailed, until all the way at the bottom you're finally doing the actual hardware work, programming work, whatever. And then on the way up this side of the V, you're verifying what was done at this step. So all the way at the top, system demonstration and validation, you're actually validating your original requirements. This is so important that for the next class, when I continue this lecture, we're going to go on, and actually we're going to go through the system requirement phase, and we're going to write some requirements in class, but that will be in the next class. Thank you very much. All right, this is a continuation of lecture number 4. So the general concept that I want to go over for the rest of this class is some of the tools that are available for you to do systems engineering, which is what you should be doing for all of your lab exercises from here on out. So for this, again, to recap, you take one whole system that you're working on and you divide it into smaller subsystems. Those smaller subsystems you can also work on and separate those even smaller. So in this case, the air vehicle has a system called the airframe, or has a system called armament. So in other words, an entire gun that you're putting on one of the wings of this air vehicle, which is part of the aircraft system. So this is very much what you are to do when we take a look at designing a system. So again, to design the system, you're going to have requirements, you're going to analyze those, you're going to allocate the functionality of those requirements, and then you will actually design and implement whatever your system is. Keeping in mind that the whole time, you're always optimizing, controlling, and analyzing your system. And if you remember, I mentioned that I do have, or have worked with people in the past who were systems engineers. This is both at NASA and Ericsson and at IBM as well. And those people typically had a good view of the entire design of a product. Some of them had multiple degrees in multiple disciplines. They had both mechanical and electrical degrees, or electrical and computer science, or something along that lines. So, if you think about everything having to do with a system, take a look at the aspects of, oh yeah, you have documents. How are you going to organize those documents? You will need requirements stored, you'll need your materials list, your designs, your CAD drawings, your program listings, your documents, configuration management, etc. So a systems engineer will have to make sure that that is in place. The other is there will be different types of things that will drive your design. In other words, are you trying to make it the most cost effective? Are you maximizing or minimizing the time to market? Or are you going to put out the best performing device ever? Acquisition strategy is another aspect of the system. Do you buy a subsystem or do you build it? Very often it's a lot cheaper just to buy something from somebody else. They call that OEM, right? Original Equipment Manufacturer. Hardly anybody builds hard drives anymore except for maybe like 3, maybe 4 companies. So you buy it from one of the companies that you know that will do a good job. If you're building a computer and you want to concentrate on the computer board, you buy this part from here, that part from there. That's what Dell did originally. Dell did a very good job of buying bits and pieces from a whole bunch of other people for a lot lower price than one could do it onesies or twosies. And they put together systems relatively cheaply and undercut IBM tremendously. You have interface controls. And keep in mind that the biggest problem with systems engineering is to identify your interfaces. Hardware, board, and a cable needs to plug in. You need to identify all aspects of that. That would be the mechanical interface. That would be the electrical interface. It would be the functional interface, as well as different pieces of software will also have some sort of interface. Maybe you have a communications cable coming into your device. You need to have and identify which sort of communications protocols interface you're going to have between the outside world and your device itself. Choose one. There's lots of standards. And then, of course, everything has to do with budgets. In the end, it's either money, time, power, space. There's a whole bunch of different things that you need to worry about when you are building a system. Now, in most cases, the mass doesn't matter, right? Because almost everything is terrestrial. However, if you start going extraterrestrial, in other words, if you're sending up a satellite, now you have to really worry about how much that thing weighs. Again, the revisit of this is that we have a big concern, or we have a nice design and a concern of top-down. So in other words, the big requirements. From those requirements, then you identify further system requirements. You allocate and specify, design each individual component, and then, of course, in the end, fabricate. And then going back up the V design, then you worry about validating, in this case, individual components that you design. You're integrating and verifying the performance specs and build verification. So let's take a look at one of our tools. You probably have seen this before, and that is a work breakdown structure. Simple. Our top level is crew launch vehicle. Kind of sounds like something like a space shuttle, right? So the crew launch vehicle includes crew and a launch vehicle. That's pretty innovative, isn't it, huh? And then you look at, what are the parts of that launch vehicle, and it will be the first stage, the upper stage, and the upper stage engine, just as an example. And there's a whole bunch of other things that will go on. Well, if you want to take a look at what's in the upper stage, you need avionics. Avionics is the term for electronics and typically software, but I see they've broken it out, is the word for electronics, control boards, etc., that will go into your vehicle. They have separate software. They have separate test hardware. By the way, don't forget, if you're going to be doing an upper stage, you most likely will be building a simulator as well. Because the first time you test your software is not when you launch it into space, all right? The first time you test your software is usually on some sort of simulator. And in fact, I should probably show you an example of this. In fact, I will. So, when I worked for a company, small company called IBM, have you ever heard of them?
Really?
Maybe. Not really.
Yeah, maybe.
They used to make computers, right?
Yeah, they used to make computers, as a matter of fact. That's another example of a company adjusting their lot in life. In other words, they realized that they were not doing it was a tough market to be in. So what is IBM doing almost exclusively now?
Business consulting.
Consulting, services, software, solutions. Because, a lot of companies in India, China, Southeast Asia, they can make cheaper hardware.
No overhead in consulting.
But you know what? It's really hard to find good consultants that could solve your problems. By the way, today we're going to continue 6/7/2012. And so I worked in the space shuttle program. So in the space shuttle, and this is where my memory starts to fade a little bit, they had 3 computers. And then they had this other backup computer. These were done by IBM. This one was done by, I think, Rockwell. And the way the computer system would work, this is Space Shuttle early years, is that all of these would run the same exact software, exactly the same. And then they would vote basically on what would happen. And they would be in lockstep. And why would you want to do that? Why would you want to have 3 computers run the same exact thing and then they kind of like vote or make sure they all did the same computation.
Verification,
Okay, verification,
redundancy.
redundancy. Why do you need that?
To make sure that it's gonna work out the way it's supposed to whenever you.
All right, work out the way it's supposed to, safety,
Failure is not an option.
failure is not an option. Yeah, you think about it, when you're in space, you really don't want to like lose your computer totally, especially when you're in like liftoff. And the computer is actually controlling things like the firing of the engines. So what they had was 3 computers. By the way, what could cause a failure anyhow?
Electromagnetics.
Solar
Faulty
radiation.
hardware.
So the biggest thing was solar radiation.
Nanoparticles.
Causing faults. So they wanted to ensure that a stray cosmic ray would not change the couple of bits in a piece of data to go from 8-9 hex to 1-9 hex, which might have catastrophic results. And so they would do their computation and vote. Well, think about this. These are not PCs that you're running here. These are a specialized system, all right? So what you would have is a test system.
Gonna see.
So your test system was really just like, it was a big IBM mainframe. Which would have a connection to your shuttle computer. And you would actually run on the hardware, but you would have simulated inputs and outputs. And they would only run one of these computers when you were simulating it, because why?
Power?
Almost all the time it would run with one unless they were testing some of the operating system software. And why would you only need to test one?
Because it's just one that you're gonna take up.
Right?
They're all exactly the same.
Well, they're all exactly the same on the shuttle itself. Not too many cosmic rays get through the ozone layer, right?
Yeah.
So there's less of a chance of failure here on Earth. And it's also a little bit more controlled because it's simulated.
Yeah.
By the way, this is before big simulators were available with GUIs and things like this. So this is in the old days, you know, with old farts running software. Remember back in the 1980s? Remember 1981? Yeah. When some of you were like 2 years old, right? Or not born yet? All right.
Yeah, not even close.
So, gosh, now I've forgotten everywhere where I was going. What was this?
Systems engineering.
Avionics software. Oh, okay. I was talking about integrated test hardware. So in this case, in our systems engineering, you not only are you building the system, but you are building the test system, right? And that means you have to identify different types of interfaces, because obviously you're not going to have a shuttle engine in your office that you can test against. So you have to build some sort of simulator, LEDs, motors, whatever you think would be needed for that. All right? Is that still? Oh, jeez. Okay, stop. Going back to where I was. So here we were, work breakdown structure. The important thing to note is that this is a great way, hierarchically, to identify what has to be done. Sub-assemblies, and you could expand on every single one of these. Integrated avionics, let's say you expand that into something that might even look all the same. But the nice aspect of this is you can identify how things are to be built, assembled, designed, purchased, delivered, whatever you want. The next is what we call a CONOP, or concept of operations. This is an example of a spaceship, but you can also imagine it's going to be the same thing, a concept of operations. For example, if you have something like this, what do you think you would have as a concept of operations?
Communicating with another?
It could be, you could show communications between two. What else?
Talk and text.
Say that louder.
Talk and text.
Talking text?
No, talk and text.
Talk and text?
Communicate with towers. Satellites.
Receive signal connect to internet.
Paperweight. I'm thinking of more concept of operation. You show one screen. When you press a button, the screen goes to look like this over here. You press another button, it goes to look like this one over here. Another one over there. So that's another example of how you would typically describe a concept of operations. It could be very low level. This one is a very high level one. I hope most of you have seen this in your earlier design classes, right? Who has not seen this before? Who is not going to admit it, right? So if I ask somebody here to explain what this is, everybody will be able to do that, right? I'm going to pick one random person and ask you to explain it. So again, I'll ask, does anybody not know what this is?
I didn't say that.
You big old liar. All right.
I haven't seen it.
Are you serious?
Yeah, but this was 97 when I came through, so it might have changed.
I swear it had this back end, like, the intro to engineering.
I believe this was Intro to Engineering, and I know Mechanical does it, Senior Design does it.
I mean, like decision matrix?
Decision Matrix, that's all this is. Right? See? Decision factors. So the whole idea is you're giving a weight and a value to different things. So, for example, if this is range, speed, payload, what does that sound like?
Rocket.
Rocket, something that flies, right? And these are the 4 different options, and oh, by the way, here's the utility value of this and the weighted value, because that's your weight, and then you add them all up, and whatever has the highest value, looks like this is your best choice. And you can do that, this is at a high level. You can even go so far as to, let's say you're building a robotic system, and you want to identify a microprocessor. Identify 4 microprocessors, and do the same study for just microprocessors. And then development tools, and on and on and on. So as another example, you can everybody know what CubeSat is?
No.
CubeSat is exactly what it sounds like, a cubic satellite. And they're what we call microsatellites. Some of them are about only a foot by foot by foot. And they have been sent up on shuttle missions and other missions. They just pop them out there, they do all sorts of stuff, and they usually don't come back. All right, so. And let's say I'm going to do a comparison of a microcontroller versus an FPGA. Which one do I want to put on my next cube satellite? And you identify a grade associated with it, and of course the weight, and based on whether or not it's tolerant to radiation, what its cost is, how much it takes to program, or for that matter, can you reprogram it in flight? By the way, this is not all that correct, because they do have some FPGAs that actually do really well in space for being reprogrammed. In fact, most everything that now goes to Mars is like that. And in the end, they do the analysis, and the weighted score is such that, look at that. It's better to have a microcontroller for their CubeSat. It's another example. Function block diagrams are pretty standard in electrical engineering. For those of you mechanical engineers, you may have something similar. Yours is more like a 3D breakout of things, right? So it's not so much a tool that is used to give you a low-level investigation into your product or your system, but you're trying to organize it. Now keep in mind that this right here can be clicked on, for example, and you can find an awful lot more of detail about that. And it may be a full system anyhow, and clicking on it shows you that it is a subsystem and all the parts below that. But this allows you to organize your computer system or your, in this case, a satellite system. I've talked earlier about interfaces, and so an interface design document is always useful for saying, what is my A and my B going to be? Don't give me all this detail, but just tell me that it's going to appear like this, something simple. All the details about what's inside that black box can be documented somewhere else, but it's not important for the interface. But it is important to know that if I have this device right here that I'm designing, and somebody is designing something to hook up into that, they really want to know what this is. So you design the interface document and you don't change it because they're designing to what you say it's going to do. And that's the important aspect. Oh, by the way, if you do change it, you have to get the other person's commission or the other part of its permission to make the change, because they have to design to it as well. So a good defined interface control document will allow one to test something without having the other real part there. And so if you saw the example, if we defined our shuttle computer really well, and we knew what it would control, so for example, I knew that, hey, these output lines here actually go to engines. I don't have to have a real engine there hooked up into my test device to be able to validate it. All I have to know is that what I say is going to happen here is what will happen in actual testing and implementation. Another example, in an interface control document, you can even go so far as to say, all right, here's a pin, this is the voltage range, this is what it's going to do. This is another tool in your systems engineering box. Here's an example of a communications interface control document. We have everything. What does this kind of look like? Oh, it kind of says it what it is inside, right? RS-232 serial communications. Now remember I said earlier that there are some designs that have to worry about how much mass and how much space it's going to take up. Obviously, if you're working with something like this, you're going to have, what kind of budget do you think you're going to have for this? Does space matter?
Yes.
Yeah, it probably makes a difference. Do you think mass matters?
Yes.
A lot or a little bit? How about power?
Yes.
All right, so what's more important, space or power?
Power.
What's more important, power or weight?
Power.
What's more important, space or weight?
Space.
All right, so there you have your requirements with respect to what has more precedence over the other. And so you can build up a spreadsheet like this. This shows mass, but you can just as easily show how much does the I squared C consume, and how often is it going to run? How much space is taken up by memory? How much time or how much power does it take, etc. Yes?
How do you decipher between when mass and power have been changed?
Why do you have to, okay, question is, when do you have to determine what is the three of your priorities, right?
Like when would you, because at a certain size, mass is going to be too big for the power. Like power is going to I'm like, I want a huge cell phone in my pocket, just because can last 10 days with it. So where does that?
Well, the assumption is, of course, that newer parts are going to be smaller and
Alive.
consume less energy, right? So for,
Unlike,
at least for us in our business, most of us in our electrical and computer engineering, newer means smaller, means less power requirements, right? So in that case, it pretty much is a wash anyhow. And I can't think of any situations where something is bigger but draws less power. I actually can't think of any.
Or weight? So
I can't think of any examples. So, did I answer your question?
Yeah.
Okay. Oh, here's an example of the power budget. I actually have used this with cell phones, where we had to identify. In fact, we had one situation where there's our processor up here. Here's a processor up here, and we were using an ARM processor, and it turned out that we had to identify: do we speed up the processing of the phone and consume more power, versus go to a new part that costs more, versus keep it running slow and not being able to handle everything. By the way, in the end, it turned out that we sped up everything, and then we improved the software as well, and we still kept everything sped up because we had lots and lots and lots of battery life left over anyhow. All right? We'll see if I go into this or not. So, failure mode and effects analysis is something you probably do lots, right? In the mechanical world, this is something that is done extensively to find out what you can do to make things fail. We do this in the software world. What do we do this? Or how do we do this in the software world? Embedded systems people.
Debug. Debug.
Okay, not only debug, but how do you debug?
Test bench?
Test benches, test cases. You throw all sorts of different inputs to it just to see if there's a point where it fails. Or you may give it a lot of traffic and see if it fails. What would you do in the electrical world?
All kinds of crazy EM stuff and build the test.
Crazy EM,
High voltages, low
high voltage.
hyper testers.
There's also a common one we did especially in mobile phones.
That's the one for the signal.
Static, yeah.
Sit. And there were specific tests to validate that it would work. We would do the simulation as well, and then we would also test it with hands-on parts. And they sell specific tools that you can generate exact kilovolts of equivalent to static and send it in the bottom of your connector and make sure that you didn't short out your entire phone. So, summary. Systems engineering, it's a process, it's an approach. It is a way you should be looking at all the products that you do in the future. So the systems engineering is something that's typically done in all of your projects, and a system engineer, him or herself, is somebody who usually has good knowledge in at least one of the disciplines working. A good systems engineer will be one of the leaders of your independent or individual disciplines working on a larger system that is called on to pull together and coordinate between all the different types of disciplines. The big way to do that is to decompose a problem and then make sure to do your design with decomposition. So, by the way, in the slides which I will post, 8 rules for prototyping. I'm not going to go over these, but you can take a look at those in your spare time. And just for grins, keys to holding a successful meeting. These also will be in the notes. You can feel free to read these at your heart's content. All right? In fact, here's one important aspect. Number 1, invite the right people. Don't invite everybody. and start with a written agenda and only address that agenda. Don't just talk because you want to talk. And it's also recommended, what's the ideal time for a meeting?
35 minutes.
Not in the evening.
Okay, who votes an hour? Who votes an hour and a half?
Hour less.
30 minutes.
They usually say an hour or less, and actually people are moving more towards 45 minutes max.
Yeah.
All right, so I am actually going to have you do an exercise in class. This would be very helpful for your future lab and or exam types of operations. So, in groups of three, I want you to identify some requirements for me. So the general idea is that I'm going to have a vehicle will roll over or travel rough terrain pull a trailer with instruments in a fashion similar to cutting a lawn. So just to recap, cutting a lawn. What does that mean? Typically, when you cut a lawn, you want to do what with the lawn?
Cut.
Cut. That's one aspect of it, all right? What's the other aspect of
Cut
it?
like the
Ooh, everybody talking at one time. One at a time. Let's see. Yes.
Make it all even.
Okay. Make it even. How do you do that?
Cut all of it.
Cut all of it.
Exactly.
By the way, this goes back to, do we want to do it like a Roomba?
No, it's a
No.
All right? So it is probably best to, by the way, I didn't put that in my requirement on how to make it run, right?
Correct.
So that could be one of the requirements. So in other words, you want to travel every single part of your area that you're supposed to. And, oh, the other thing I'll need to add on to this is that there are occasionally 4-inch and larger trees diameter
So we probably can't just talk about
trees in the field. All right?
That's a pretty big tree.
Damn.
Well, 4-inch, that's about big. They cut everything else down. Everything else they cut and pull away. All right? This is a real world problem, by the way. I have a vehicle called Zapatabot, right, that is supposed to do this. Can't do that yet, but it's close. So, your task. We're going to identify using some of these skills we just learned. We're going to reduce our problem, right? Let's see a good example. I guess I will have to go back to this. We will have to reduce our design or our device and write some requirements. So what do you think the first step is going to be?
Define the parts.
How big is the field?
All right, we say design parts. Would this be more design or identify?
Identify.
So what are our major parts?
Motor, blade,
Wheels.
Locomotion. Movement.
All right, so we're going to have vehicle.
We can't see it.
Tower.
Motion.
I put that in vehicle.
Okay.
Or I put that in powertrain.
How are you going to protect the instruments?
Protect.
Grass.
From what?
Like,
chassis.
to you gotta figure out like what do you protect the instruments that you have to keep safe?
Did we design the trailer or is the trailer design?
Trailer's design, you don't have to worry about
Oh,
it.
we gotta
Oh,
just
okay.
pull it. Probably it's supposed to be.
There. The trailer is a box with 2 wheels and a trailer hitch,
Sensors.
which is 48 inches wide and what is that there? The height is 12 inches of clearance. So what's the other, and it doesn't matter how long it is.
Sensors.
Sensors, is that
Yeah.
big enough? And remember, we're doing top down. What would be a bigger part than sensors?
Control system.
All right, control system.
So if we don't know how long it is, how we'll know when we clear the trailer?
All right, I'll give this to you.
That's my guess.
72
The
inches
trailer
from the
always
very
falls
back to the end of the tongue. Can you think of any bigger part of this entire system?
Equal powertrain.
I'm guessing software be inside the control system.
Well, you could say it is, and so we'll assume that that software is inside of that.
Maybe 3.
Oops.
They're nasty, they overcomplicate everything.
Anything else?
They wouldn't be.
Do we care about personnel?
There's a ton.
Is this interface part of like control system?
You mean like screens and stuff like that?
Yeah.
Yeah, it could be part of that. How do you know where you are?
GPS.
GPS.
Remote view control system.
Is GPS something you control?
Nope. Oh,
Answer is yes.
Oh yeah, because you can
In
fake your
some
position.
respect.
You can use it to control yourself.
Your car GPS, by the way, knows you're driving on a road because
A map.
it has maps.
Oh, that's nice.
And its accuracy is really not that good. 50 feet maybe, maybe 30.
Yeah, kind of like the one time when I was looking at the GPS and I saw I was over on the side of the road.
All right? I think those are the big ones I'm going to look at. So my request to you is let's expand this one. And so now your assignment right now between your group is 2 assignments. And I think I'm going to make this a quiz. Further reduce control system. I want you to turn in, you will turn in 1 sheet of paper that has that on it
For one sheet
Control.
for your group.
How many parts? You care?
For the control system, I don't care how many parts.
Okay.
All right? So those of you in video land, you can feel free to pause and do this on your own. We'll get back to you in a few minutes. All right, can I have one example that somebody would like to show me what they did? For a trip to the prize closet.
Oh yeah, I saw you.
We all get together, 3 of us?
Too funny.
Sure.
All right, what's the first chance at Jimmy John's? Of showing what they did.
Y'all got to every day you got
All right, give me, bring, come on. Prize closet. Don't I have good stuff there?
I think Jackson has some I can't see it.
All right, here's an example, and they identified 3 aspects of the control system: sensing, decision-making, actuation. So they actually split it into functionality, not a piece of hardware first, which actually is pretty innovative, it's pretty neat. I give you A+.
Smiley face.
Smiley face.
Star.
This part.
With a golden star.
So I will get, I'll take a picture of this a little bit later. All right, that looks good. Oh, going on, okay, sensing, GPS, LiDAR, FPGAs, microcontrollers, and what they're doing. Okay, interesting enough.
Here the things.
No, thank you.
The control by the GPS.
Will be
So, we were looking at design and identify parts. The next step in this would be to actually write requirements for our system. So if we were to look at an example of some requirements, let us take a look at vehicle as a requirement. All right? So I'll say so what I'm doing is I'm breaking this out in a system manner and identifying one requirement for vehicle. Vehicle will be, the vehicle shall be able to run in sun, rain, snow. Notice I'm not solving the problem. I'm not saying, oh, and it must have knobby tires. I'm saying it must be able to do this and this and this. All right? The vehicle shall operate in the temperature range of negative 10 degrees Celsius to 50 degrees Celsius. I don't know, is there a place on Earth that you can find? Yeah, there's a lot that you can find at 50 degrees Celsius, right? I'll change that.
Man.
So 50 degrees Celsius is only, what is that? I can't do the math. Let's see, 180, 90 degrees, 90 plus, that would be 122 degrees Fahrenheit, right? Would be 50 degrees Celsius. Is there anywhere on Earth that gets that? Pretty much deserts, right?
Yeah, tennis court on a hot day.
Yeah. So putting it up to 60 degrees is pretty good. Yeah, I think some of the deserts get into like 130s, right?
Yeah.
Give me another example of something it should be able to do.
There be a size requirement?
Ooh, vehicle. Shall be no larger than, what's 48 inches in metric?
90, 170 something.
That's not. I know.
48 inch.
A little over a meter. Go. Damn Americans.
Now, notice I did something here that you already see. What is one thing I've done? Not only categorize it, but I'm being consistent with my units.
SI units?
Yeah. You know, I could have used English, I could have used SI. SI is the measurement of what? Science, right? Have you heard about one of the problems, one of the biggest failures of system engineering? One group for a NASA space probe to Mars worked in English, the other worked in SI.
Oh no.
And the coordination between the two was not too good, and this is one of the ill-fated Martian visits from 5 years ago or so, where because of the difference in units, the probe actually smashed into the Martian surface at a great speed and basically is inoperable because it's in lots of little pieces. So that is an example. And if I were to say powertrain, the vehicle shall operate for 8 hours continuously. Can be powered by gasoline or electricity, battery. Just in case they think that you could hook up a extension cord and run this, I made sure to put in their battery. So your goal, should I write one for you for control system?
Sure.
And this is more of an operation, but the system shall be able to control its location with an accuracy of 2 centimeters. That's pretty amazing, isn't it? And actually, that's one of the requirements of the system. So, your second part of the quiz is to write 5 good requirements for the control system.
Do we get to use that one? Shit.
More control, more requirements. Write 5 other good requirements.
Hey,
Yes. Your break is while we sit around and do all this stuff. All right, so spend some time and do that now. So, the assignment, 5 other good requirements for the control system. And so here we go. Here's an example. I'm going to have to zoom in on this one. So, the system shall be able to detect obstacles within the path of the vehicle. That's a good one, right? Manual drive override via remote user interface. That's a pretty good one too. Shall record previously locations for mapping. I'm assuming there's a word in there somewhere, but you know, that's good enough, right? Shall avoid obstacles larger than 0.1 meters by 2 centimeters. Shall require negative 165 dB for what? So I guess for GPS navigation. All right. So you know, this is an example of how you would write some requirements. Again, requirements words. The system shall. System shall. You could have said the control system or the control shall. So this will be something that you will definitely be tested on. I'm glad you learned it. Thank you very much. This is it.